Hi, welcome to Lecture 10 of the online course on Explainable Machine Learning and Artificial Intelligence. This lecture will be about evaluating explanations. Throughout this course, I have insisted on the importance of evaluating the explanations produced by different explainability methods. Exactly how to evaluate explanations is, however, an open question and a topic of very active research in the field. Currently, we simply do not have very solid standards for evaluating explanations. So in this lecture, we will cover some of the existing ideas and a couple of recent studies that aimed to evaluate explanations. The specific goals of this lecture will be to first identify the key issue with evaluating explanations, second, distinguish different approaches for evaluating explanations, then review a couple of recent studies on evaluating explanations, and finally discuss open challenges and current practices. The central question of this lecture is really how should we and how can we evaluate explanations? To address this question, the first step is to remember what we are trying to achieve. Explainable AI seeks to produce explanations for the outputs of AI and machine learning models with the goal of ensuring reliability, safety, trust, fairness, and lack of bias in the underlying algorithms. The key issue is that it is very hard to evaluate how well these goals are reached, because we do not have a clear and quantifiable ground truth. If we want to quantify how well an algorithm classifies images, we have a clear performance metric and a loss function that we can optimize. This is simply not the case for explainability. Explainability precisely seeks to address the problem that we don't know how to quantify and optimize safety, trust, and fairness. So, how can we evaluate explanations produced by one of the methods we covered in previous lectures? Two general types of approaches have been proposed. The first approach is to try to design a quantifiable proxy for a metric of explainability, and then automatically apply this proxy to evaluate explanations provided by an algorithm. We have already seen some examples of this approach in the previous lecture on saliency maps. One way to evaluate saliency maps is to remove from the original picture the features identified by the saliency map, and then compute the classification accuracy. That's one example of a quantifiable proxy for explainability. In this lecture, we will see another example. The second approach is to evaluate explanations through experiments with human subjects, but by asking them to subjectively quantify the quality of explanations. This can be done at different levels, with different types of subjects performing different versions of the task. The starting point is to ask domain experts for detailed feedback on simplified tasks, then turn to more systematic feedback on the real task that the machine learning is solving. Finally, one would want to quantify explainability with actual end users performing the full task. In this lecture, we will discuss some examples of studies that evaluated explanations with human subjects. Let's start with an example of a study that evaluates explanations via a quantifiable proxy. This study was called Fooling Lime and Chap. This is the title of a paper published by Slack and colleagues in 2020. The goal of this study was to evaluate whether local post hoc explanation methods, such as Lime and Chap, provide a reliable and robust protection against discriminatory biases. This is particularly important for applications such as crime prediction or credit risk prediction. More specifically, this study asked whether malicious actors can fool the post hoc explainability methods and generate black box models that hide biases. Here is the setup of the study. The study starts by assuming that an adversary wants to deploy a biased black box classifier for a critical decision, such as parole, bail, or credit. This adversary knows that it must provide the access to the black box models both to customers and to regulators, who can then use post hoc explanation methods to try and understand it, and in particular to assess whether the black box model is fair or biased. In this scenario, the goal of the adversary is to fool the regulators and hide the biases on which the black box model is actually based. The key question of the study is, can this be done? Or are post hoc explanation methods robust enough to detect any bias? The main message of this paper is that an adversary can in fact fool explanation methods and hide biases. The authors showed that this can be done in particular using an approach they called scaffolding. How does scaffolding work? Remember that to approximate a black box, Lime and Shap generate random synthetic points around an input instance of interest. The key point is that these synthetic data points do not in general match the true distribution of the data that the black box uses. In particular, if the black box can detect the inputs as being synthetic rather than belonging to the true dataset, then the black box model can provide a different response to synthetic data than for true data. In this way, it can fool explanation methods and potentially regulators. To illustrate this, the authors of this study took as an example the COMPASS dataset used for crime prediction models. They then compared the data points in this dataset with synthetic, perturbed data points generated by Lime or Shap. This figure shows a low-dimensional projection of the data on the two principal components. Points from the original COMPASS dataset are shown in blue. Synthetic data points generated by Lime are instead shown in orange. We see in this figure that the points from the original dataset follow a very specific distribution. This is often called the data manifold. Instead, the synthetic points have a different, much broader distribution. They do not belong to the data manifold, but are often on directions orthogonal to it. If a black box model can detect the synthetic off-manifold inputs, then it can produce different outputs for them. This study precisely shows that this can be done. The authors showed that it is possible to build an adversarial model by first detecting whether a point is within the data distribution or outside. This can be done using a built-in classifier to detect inputs that lie outside of the original training distribution. Then, if the input instance is within the distribution, the black box model produces a biased output. If the input instance is outside of the distribution, the black box instead produces an unbiased output. The study by Slack and colleagues applied this approach to several real-world datasets. Each of these datasets contained a sensitive feature, and typically the goal of explanation methods such as Lime and Shap would be to assess whether a black box algorithm is biased with respect to that feature. Let's look first at the COMPASS dataset, which we have discussed in previous lectures. This dataset consists of data on prison inmates in the US. It contains features based on criminal history, demographics, jail and prison time, and the goal is to predict the risk of future crime. For this dataset, the sensitive feature is African American. The authors also used a second dataset on crime called Communities in Crime. Here the goal was to predict the risk of violent crime in a neighborhood, and the sensitive feature was the percentage of white population. They also considered a dataset on credit rating, where the goal was to predict the quality of the credit customer from input features based on account information, credit history, loan purpose, and so on. For this dataset, the sensitive feature was gender. The authors then used these three datasets to conduct an experiment aimed at testing whether an adversarial actor could fool algorithms designed to detect bias. The experiment was based on 3 steps. The authors first constructed a biased model that is perfectly discriminatory, meaning that it produces an output based only on the sensitive variable and no other feature. They then generated perturbations of the dataset to train a classifier that detects out-of-distribution inputs. Finally, they incorporated this out-of-distribution detector in the black box so that each time an out-of-distribution input was detected, the black box model generated a perfectly unbiased output. This unbiased output is produced using input features that are not correlated with the sensitive feature. In the simplest example, the authors used a single uncorrelated feature, but they also examined what happened when they used 2 uncorrelated features. The goal of this experiment was to quantify how well this works. Specifically, how well can a classifier detect out-of-distribution points with respect to a real-world dataset. This figure shows the results for the COMPASS dataset. The 3 columns show the result of applying LIME to 3 different models. In the first column, LIME is applied on the bias model without any detector of out-of-distribution inputs that would fool LIME. This is the control case. In the second column, LIME is applied on the adversarial model, which detects out-of-distribution inputs and produces unbiased inputs based on 1 uncorrelated feature. In the third column, LIME is applied on the adversarial model based on 2 uncorrelated features. In each case, LIME is applied to a large set of inputs. For each input, LIME then classifies features according to their importance score. Each column shows in red the percentage of data points for which the sensitive feature appears in the top 3 most important features, while blue colors show the percentage of occurrence of the 2 uncorrelated features used to build the 2 adversarial models. The first column shows that without adversarial attack, LIME detects very consistently the sensitive feature as the most important feature in the model. In this control case, LIME therefore does a very good job in detecting the bias in the model. The second and third columns, however, show that when an adversarial out-of-distribution detector is built within the model, LIME is completely fooled. It does not detect bias at all anymore. This was the main result for LIME. This evaluation shows that it is very vulnerable to out-of-distribution detectors. The others performed identical analysis for SHAP. This figure summarizes the results of an identical assessment for SHAP. Again, the first column shows that for a black box model without an adversarial out-of-distribution detector, SHAP does a very good job in detecting that the model is highly biased, as it detects the sensitive feature as the most important. The second and third columns showed the results of applying SHAP to 2 adversarial models based on either 1 or 2 uncorrelated features. If a single uncorrelated feature is used, SHAP still detects very reliably the sensitive feature as the second most important one. If 2 uncorrelated features are used, the results of SHAP are a little more mixed, but it still detects the sensitive feature very consistently among the first 3. So altogether, SHAP appears to be more robust than LIME and more reliable for detecting bias. This was an illustration of the results obtained by comparing LIME and SHAP on one of the 3 datasets used in the study. The 2 other datasets show very similar results. To summarize, the study by Slag and colleagues evaluated the robustness of LIME and SHAP with respect to adversarial attacks designed to deliberately hide the bias present in a black box model. Altogether, this study shows that LIME and SHAP are often very vulnerable, and this raises the question of how to build adversarially robust explanations. More specifically, the study points out the importance of taking into account the distribution of the input, also called the data manifold. This study was an example of the first approach to evaluating explanations based on building a quantifiable proxy for the quality of explanations. We will now turn to the second approach for evaluating explanations, which is based on user studies, experiments with human subjects. User studies aim to directly ask human subjects how useful are the explanations provided by an explanatory method. Several types of user studies have been tested in recent research. The first type of studies focus on debugging. They aim to quantify how effective explanations are in helping users to identify erroneous algorithms. The second approach is to examine so-called forward simulations. This type of study asks subjects whether they can predict the output of the model for a novel input instance, based on an explanation of the model. Concretely, a subject is given a set of input feature values together with a set of model explanations, such as importance scores. And the study then measures what type of explanations allow users to make the best predictions. The third approach is counterfactual reasoning, which is a variant on forward simulations. Subjects are given an input together with a model output and an explanation of this output. They are then asked to predict an output for a perturbation of the original input. In the rest of this lecture, we will look at two examples of user studies of these different types. We will start with a study that focused on debugging. A study published in 2020 by Adebayo and colleagues aimed to evaluate how effective saliency maps are for debugging. This study focused on convolutional neural network models performing image classification and introduced bugs of different types in this black box model. The goal was to test how well human subjects can detect those bugs based on provided saliency maps. The rationale is that this is one way of testing the explanatory power of saliency maps. In this human subject study, the participants were asked to act as quality assurance testers for a company selling animal classification models, specifically models designed to distinguish birds and dogs. In each test, the participants were shown the original image, the model prediction, and the corresponding saliency map. They then rated the quality of the model on a scale from 1 to 5. They were also asked to provide a rationale for their rating. This was a multiple choice question with possible options such as wrong label, correct label, expected explanation, or unexpected explanation. This was the general design of the study. They applied this approach to test for different types of bugs and different types of explanations. To categorize different types of bugs, the authors went back to the model development pipeline and identified three possibilities. One possibility was to introduce bugs by contaminating the data. Concretely, this means that either the model is trained with mislabeled inputs or spurious correlations are added. For example, specific types of background were added to specific classes, such as blue sky backgrounds for birds or forest backgrounds for dogs. Another possibility was to add bugs directly in the model, either by randomizing some of the weights in the model or by freezing some of the layers during training. Finally, a third type of bugs was added at the test stage by using a model that was trained on a totally different type of data, for instance, fashion MNIST. To compare different types of explanations, the subjects were given saliency maps generated by different methods introduced in Lecture 9: vanilla gradient, smooth grad, and integrated gradients. These panels show three examples of inputs to the model and saliency maps produced by the three different methods based on a normal model without bugs. However, if the model contains bugs, can saliency maps be used to identify them? This is precisely what this study aimed to assess. Here are a couple of examples of saliency maps produced by a model in which the top layer was randomized. And here are a couple of examples of a model in which spurious correlations are added in the background. These examples suggest that it might be possible to identify some types of bugs using saliency maps, but perhaps not others. This might also depend on the type of saliency maps. So, beyond looking at a couple of examples, a systematic quantification seems important. And this is precisely what Adebayo and colleagues collected in their user study. As a reminder, the first question the subjects were asked was to rate each model, specifically to give a score indicating how likely they would be to recommend the model. This figure shows all the results. The different rows correspond to the three different methods for computing saliency maps: vanilla gradients, integrity gradients, and smooth grad. The first column on the left is the normal model without bugs. The other columns show results for models in which different types of bugs were introduced. The main conclusion from this figure is that the subjects clearly gave lower ratings to models with bugs compared to the normal model without bugs. So the subjects were able to detect the bugs when they were present in the model. But the key question is, how did they detect the bugs? Specifically, did they use the explanations provided by the saliency maps? To assess this, remember that the subjects were asked to provide the rationale for their ratings. This figure shows the rationale provided by the subjects for their ratings. As in the previous figure, different rows correspond to the three different methods for computing saliency maps. The first column is the normal model, while the other columns are models with different types of bugs. Each subpanel shows histograms for different types of responses provided by the subjects. Here, pink is wrong label, light green is correct label, red is unexpected explanation, and green is expected explanation. What stands out from this figure is that for 3 out of 4 types of bugs, the users reported that they detected bugs because they thought the output of the model, the label it produced, was incorrect. That's shown by large pink histograms. Only in the case of spurious correlations, the subjects reported that they based their judgment on the explanations provided by the saliency map. For other types of bugs, they did not seem to use explanation. So altogether, the conclusions of this study are that subjects did not seem to identify defective models using saliency maps, but relied primarily on their own predictions for the output. Explanations did help identify spurious correlations, but this was the only case. These observations point out, in particular, some possible limitations in the design of the human study. The task used here relied heavily on prior knowledge. The networks performed a task which the human subjects were very good at. Nevertheless, subjects reported that they were often confused by what was going on. This example illustrated some of the challenges in designing user studies to evaluate explainability. In particular, isolating and quantifying how much the provided explanations help is not straightforward. We will now turn to a second example of a human study, which focused on identifying more precisely the effects of explanations. This second example is a study published by Hayes and Bansal in 2020. The goal was to design a human user study that allows to isolate the effects of explanations on the subject's ability to mentally simulate the model and predict its output. The approach they developed was to first separate explained instances from test instances and then evaluate the effect of explanations by comparing explained instances against a baseline of unexplained examples. The authors focused on 2 machine learning tasks, a text-based task, a sentiment analysis in movie reviews, and a tabular task, the classical adult income data, where the task is to predict the income of a person. For these 2 tasks, the study compared 5 different types of explanation methods. The first one was the classical LIME approach. The second one was based on interpretable rule lists. The third one was based on prototypes, a type of explanation based on providing examples. A fourth method called decision boundary was designed specifically for this study. We will not go into the details here. And finally, the authors considered composite explanations that combined all four methods. Here is an example of an input instance and model output that the subjects were shown in the sentiment analysis task. The input is an example of a piece of a movie review. Despite modest aspirations, its occasional charms are not to be dismissed. In this case, the output of the model, y hat, is that the review was negative, while the correct output y is that the review was positive. The subjects are then shown an explanation for the output of the model, for example using LIME. LIME identifies feature importance scores, or contributions, for different words in the sentence, and shows the words with the largest scores. For this example, charms and modest had positive contributions, while dismissed, occasional, and despite had negative scores. LIME then summed the scores for these words and compared them with a baseline. For this instance, the sum was below the baseline, and this provides an explanation for why the original model predicted that the review was negative. This was just one example of inputs, outputs, and explanations provided to the subjects. A key part of the study by Hayes and Bansal was that they designed procedures to evaluate how much the explanations helped the subject understand what the model was doing. In fact, they designed two procedures. The first procedure aimed to quantify the effect of explanations on forward simulations, specifically how well the subjects can predict the output of the model. This procedure consisted of 4 phases. The first phase was a learning phase in which the subjects were given examples of input instances X, correct labels Y, and outputs y hat of the model. The goal here was that the subjects learn to predict what the model does. Importantly, in this first learning phase, they were given no explanations. In the second phase, the subjects were then tested on how well they could predict the output of the model. Concretely, they were given a set of input instances and had to predict what output the model would produce for each instance. The subjects' predictions were then compared with the model outputs to compute a score, which quantified how well the subjects predicted the model. The third phase was again a learning phase, in which the subjects were shown examples of input instances X, correct labels Y, and outputs Y hat of the model. But this time, for each instance, they were also shown an explanation for the output of the model, such as explanation provided by LIME. After this new learning phase, in the final phase, the subjects were again tested on how well they could predict the output of the model. The final result of this procedure allows to quantify the impact of explanations by computing the difference in the accuracy of the subjects' predictions before and after they were provided with explanations. This procedure was applied to a user pool that consisted of 32 undergraduate students. Each user was tested on one combination between a dataset and an explanation method. Altogether, there were 10 different combinations between datasets and explanation methods because the authors used 2 datasets, the textual and tabular dataset, and 5 different explanation methods. This table summarizes the results of this evaluation for forward simulations. The left part of the table shows results for the text dataset, while the right part shows the results for tabular data. Different lines correspond to the 5 different explanation methods that were evaluated. The N column shows the number of instances tested for each combination between a dataset and an explanation method. The main results are shown in the change columns. These columns show the change in the accuracy of the subject's predictions after they were shown explanations. To evaluate the significance of this change, the CI column shows the confidence intervals, and the P columns show the statistical p-values for the computed changes. Looking at the p-values, the only case that was statistically significant is shown in bold font. This is the case of tabular data with LIME explanations. For all other combinations between datasets and explanation methods, the effects of explanations on the accuracy of the subject's predictions was not statistically significant. This is the result of the first procedure for evaluating the effect of explanations on the subject's ability to mentally simulate the model and predict its output. In this study, the authors designed also a second procedure. The second procedure aimed to quantify the effect of explanations on counterfactual mental simulations. The ability of subjects to predict how a change in inputs changes the output of the model. This figure illustrates the details of this procedure. The procedure consists of two phases, a pre-prediction phase and a post-prediction phase. In the first, pre-prediction phase, the subjects are shown a series of examples of inputs, together with ground truth labels and model predictions. For each example, they're also given a perturbation of the input, and they are asked to predict how this perturbation affects the output of the model. This is a concrete implementation of counterfactual reasoning. At the end of this first phase, the subjects' counterfactual predictions were compared with the model outputs, and a score was computed, which quantified how well each subject predicted the model. In the second, post-prediction phase, the subjects were shown the same combinations of inputs, ground truth labels, and model outputs, but now together with explanations for model outputs. These explanations were generated using one of the methods listed before. Then for each example, they were again given a perturbation of the input and asked to predict how this perturbation affects the output of the model. This led to a second prediction score. Finally, the impact of explanations was quantified by comparing the prediction scores between the two phases. As for the first procedure, forward simulations, the output of the second procedure is the change in the subject's prediction scores after they were shown explanations. This change was computed for different combinations of datasets and explanation methods, and then the statistical significance of the obtained change was computed. The final conclusions were very similar to the conclusions of the first procedure. Most of the explanation methods did not lead to a statistically significant change. In fact, only LIME did. So the specific conclusion of this study was that LIME on tabular data was the only combination between dataset and an explanation method that led to a clear effect of explanations on predictions in both procedures, both forward and counterfactual simulations. In parallel, the users were systematically asked to rate the quality of the explanations they were provided. However, the authors found that these ratings were in fact not correlated with how much explanations actually helped with predictions. So this is a note of caution against evaluating explanations qualitatively. A broader set of conclusions of this study is that, first, many explanation methods may not noticeably help understanding how a model works. Different methods might be successful in different domains and settings. Choosing correctly the hyperparameters of the different methods might matter, and it is not clear how to do this. And finally, altogether, there's a lot of room for improvement of evaluation methods for explainability. Evaluating explainability is a very active area of research. We have covered here two examples of user studies, and these examples illustrated some of the challenges involved. Here's a brief summary. An overall challenge is to select what information to present to the subjects. Specifically, this involves selecting which explanation methods or visualizations to assess. Another decision is which variable to use for the assessment. The studies we covered assessed how the explanations affected the subject's performance or trust. Another possibility could be to study how explanations modify the time they need to produce a prediction. Then there's the technical challenge of how to select hyperparameters used in the explanation methods. And finally, there's the question of which additional information to show to the subjects. For example, whether they should be shown or not the predictions of the black box model. The overall difficulty is that making good design choices requires a combination of expertise in explainable AI and human behavior. Another important challenge is that user studies are costly. They are resource-intensive, time-consuming, they involve the recruitment and compensation of subjects. So altogether, it is very difficult, if not impossible, to run comprehensive user studies. Instead, we need to carefully select which studies to do. This brings me to the end of this lecture on evaluating explainability, and also to the end of this online course on interpretable and explainable artificial intelligence. What I hope you will keep from this course is that it is essential to better understand and explain AI algorithms and the decision that they produce, in particular for high-stakes applications. A broad range of interpretable models and explanation methods have been developed for that purpose. A general issue is that most of these models and methods still need better evaluation and validation. Nevertheless, explanation methods already play an important role as a set of fluid, social practices in the machine learning community, and I hope this course gives you the basis to use these methods in your work. Thank you very much for following this course.